right, grade 11s. We are on our last day of math, and today we're going to be talking about annuities, um, which really the big idea for those is regular payments or regular withdrawals that are happening over and over and over again, with like a steady amount of money or a consistent amount of money. So the goal for this first video is to solve future value problems where we are making regular payments or regular deposits. We're going to do the notes through the video, and then there's some practice from the textbook. So an annuity is a series of equal payments or deposits made at regular intervals, annual, monthly, weekly, so any kind of regular interval with compound interest being charged if it's a loan or compound interest being earned if it was an investment or like a savings account. The future value of an annuity is the value obtained when equal deposits are invested. So the future value is what we're going to be finding. And the idea is we put in some money and it's going to earn interest. And we're going to put in some more money, it's going to earn interest. If we add all of that together, we'll find the future value of the whole annuity. This is a way of saving for something by regularly paying into it. Some people do this for RRSPs, Registered Retirement Savings Plans, where you might have some money deducted off of your paycheck like every other week, to make it like a small amount that comes off that you can handle. Um, and this is also a way of paying off a loan, not all in one big lump, but paying it back kind of like slow and steady, like a car loan. You might pay a weekly payment towards a car loan. Okay, so there's a lot of information packed onto this slide, and I've changed the order a tiny bit from what's on your handout just to make it all fit here. But what's up at the top is like a visual timeline. So this is called a timeline. If your textbook, you see that in your textbook, that's what it's referring to. That shows you what's happening with the money. So the idea here is in year 0, we have no money, none at all. But after a year, we are going to have $1,000. That $1,000 is going to earn 5% interest, it looks like. And then by the end of 5 years, that chunk of money will be worth 1,200. 2 years from now, so it looks like we're making a regular payment of $1,000, so an annual payment. So at the end of year 2, we're going to make another deposit into the bank of $1,000. That money's going to sit in the bank account and earn 5% interest, but not for as long. So the exponent's only a 3. It'll sit in there for 1, 2, 3 years. So that chunk of money or that deposit will end up being worth 1,157 after the 5 years in total. We'll do the same in year 3, same in year 4, and then in year 5 we'll deposit the $1,000, but it hasn't had any time to grow, so it's only worth 1,000. Adding all those together, we can find the future value of the whole annuity, and it's $5,525. So this is just one example, but it's like a nice visual way of seeing what's happening with the money if we're making regular deposits. So that's what it looks like is happening here. Regular deposit of $1,000. So really you've only put 5,000 into the bank, but you've ended up getting $5,525. So you earned some good interest on it in this scenario. There's two formulas, or well, there's one formula and a rearranged version of the formula that we're going to use for this type of problem, where we're talking about future values or the final amount. So A is the final amount. That should be familiar from our old compound interest formula. A is the final amount. R is the regular deposit. So in this case, this would be the $1,000 that we're putting in again and again and again, so regularly. I is interest, and N is the number of deposits in total. So I and N and A all have the exact same meaning as with our old compound interest formula, and the only thing that's new here is that instead of having like one lump payment or principal, we're breaking it up into many small regular payments. So the formula looks different, it looks a little bit more complicated, but the idea behind it is kind of the same. On the right side of the screen, there's the same formula rearranged to solve for r. So to try to get this variable r by itself, so we've multiplied both sides by I, a times I, that's what we see here now, um, and then divided by that whole big square bracket to move it away from the r. So you don't need to know how to rearrange it. We can use either one of these formulas depending on which variable is the goal in a given question. So we will try one of each type and our examples. I just want to make note of this. I've added in the brackets. Here we've used capital A for the final amount. In your textbook, in some places you'll see FV for future value. So those two are kind of interchangeable. And here in this formula, R is used as the regular deposit or payment. And in some places, including an online calculator we're going to use, you're going to see PMT for payment. So just know that means the same thing. All right, example one. Sherry makes deposits of $50 quarterly into an account that pays 2.25% per annum. This means, remember, per annum or per year, compounded quarterly. So she's making every quarter, which is every 3 months, she's putting $50 into her account. How much is she going to have after 2 years? So the first job for any of these questions is to try to pull the numbers out of the question and attach them to the right variables. So the $50, that is her regular deposit. The interest rate, 2.25%. I'm going to change into decimal form, so dividing it by 100. And this one's compounded quarterly, so I have to remember to adjust the interest rate um, because of the compounding period. So that will become 0.00625. The number of deposits. So she was doing quarterly payments, which means 4 per year for 2 years. That means she deposited money 8 times in total. Okay, so on the left side, that's kind of like the planning part of the question, figuring out what are my numbers that I know so we can plug them in properly. So in this one, the goal is to find out how much she has after 2 years, so the future value or the final amount. So I'm going to pick that version of the formula. I'm going to write out the formula because it's complicated. I'm going to actually show it. 1 plus I to the n, take away 1, divided by I, and then start plugging in the numbers. So R is 50. 1 plus the interest rate becomes 1.00625. The exponent is 8. Whatever the answer to that power is, we're going to subtract 1 from it and then divide by the interest rate. So that looks pretty awful. You need to be a little bit careful with your calculator to make sure that comes out okay. I did break this into pieces, but in the interest of space, I'm just going to kind of say what I got. So for this square, actually no, I can move the other part of the text. Give myself a little more space. My apologies if you don't have much room on your handout. Alright, so this square bracket, 1.00625 to the exponent 8. Find that first and then take away 1. And the answer to that whole square bracket is 0.05. 110753. So I'm keeping lots of decimals. I'm not really sure how precise I need to be, so I'm going to keep extras just to be safe. And now at this point, that number 0.05110753 is still sitting on my calculator. I'm going to hit times 50 and then divide by 0.00625. So that stuff I'm going to do all in one step to get my final answer. All right, so after 2 years, Sherry has $408.86. Part B of this question says how much interest was earned. So we're going to look at this final amount of money and compare it to how much she actually deposited. So her deposits is kind of like her principal. She put into the bank $50 on 8 different occasions. So that's $400 that she actually put into the bank. Her final amount was the $408.86 from the previous question. And we can find the interest by subtracting those two numbers, like comparing them. So 408.86 take away 400 tells us she only actually earned $8.86 interest. So that's a pretty crummy investment. It wasn't sitting in there long enough to earn a ton of interest after only 2 years. If we did this question again, but with a time frame of like 10 years, she's probably making much better interest on a longer time scale. Okay. Example 2, Steve makes $300 deposits semi-annually into an account paying 4% interest, compounded semi-annually. How much money is he going to have in 5 years? So I'm going to read through that again and write down the numbers, like the given information. The $300 deposits, those are the regular payments. The interest is 4%, so 0.04, compounded semi-annually, which is twice per year. So adjusted, that comes out to be 0.02. The number of payments that he is, or deposits that he's making, 5 years with 2 payments per year. That comes out to 10 in total. So there's my planning. And again, we're trying to find the final amount. Starting with the formula to make sure I don't make mistakes. And then substituting some of the numbers in. 300 for R, 1.02, so 1 plus the interest rate inside the bracket. The exponent is 10. And divide everything by the interest rate, 0.02. Again, the calculator part of this is the trickiest. One thing I like to do, so you can do this exact same way as the last one, do the power first, take away 1, multiply by 300, divide by 0.02. So that would be the flow that I showed in the last solution. Another option is to deal with, leave the square bracket to simplify later, and do 300 divided by 0.02 first. So this time, that's how I'm going to do it, just to show you a different approach that you might like. And then there's still the square bracket left to simplify. 1.02 to the exponent 10, subtract 1 from that. The answer to that square bracket is 0.218,99442. So that looks nice. I got rid of the fraction a little bit quicker. So you can use this method if you like it, dealing with the stuff that's not in brackets first as a new coefficient. And then we're going to multiply those two things together. That decimal is still sitting on my calculator, so I'm just going to multiply by 15,000. And the answer is $3,284.92. So in 5 years, Steve has that much money. This one doesn't ask to figure out the interest, but just out of my own kind of interest, $300 payments 10 times. So he actually put 3,000 into the bank and he got out 3,200. So he made like $200 or $300 worth of interest. All of that part is interest over a time of 5 years. Okay, one last example. And this is going to be using the rearranged version of the formula. So we haven't seen one of these ones yet. It says Jamie wants to have $500,000 in an RRSP when he retires at age 60. The annual interest rate is 8%, compounded quarterly. Oh, sorry, Jamie is a girl. My bad. She deposits equal monthly deposits starting at age 28. How much do those deposits need to be in order to hit her target? Okay, so there's a lot of stuff going on in this question. Um, this time we know the final amount that she's hoping to have at retirement, $500,000, which sounds like a ton right now, but I feel like in the future, 500,000 is not going to sound so much. Okay, the annual interest rate is 8%. So that's 0.08, and it says compounded quarterly. So I'm going to divide it by 4 to get 0.02. The number of regular deposits, we're going to have to figure that one out. So how much time has passed between when she started making payments and finished making payments? That's 60, take away 28. We can subtract to find that. And she's making those payments for all of those years. And she's doing quarterly payments, so 4 times per year. So there's 32 years where she is making these deposits. And in total, that comes out to 128 of them. Okay, that's a lot of like prep work for the question. And now I'm going to write out the formula. We haven't used this version yet, the rearranged one. So I'm going to be careful to write it out properly. This is A final amount times the interest rate divided by 1 plus the interest rate, the exponent n, take away 1. So it has all the same parts, just rearranged into a different order. And now I can substitute the stuff that I know. 500,000 for the amount. The interest rate was 0.02. 1.02 is the number in my bracket. The exponent is 128. And again, there's a lot going on, so we have to be careful about using our calculators. I'm first going to simplify the numerator. 500,000 times 0.02 is 10,000. So I simplified the numerator, and separately I'm going to simplify the denominator. 1.02 raised to the exponent 128, so find that answer and subtract 1 from it. The denominator simplified becomes 11.613 approximately. I rounded that off. And then we've got a division to do to get our final answer, and it comes out to be $861.10. So if Jamie wants to have 500,000 sitting in the bank when she retires, she needs to make these quarterly payments or deposits of $861 for that whole time. Okay, so every 3 months she's gonna try to deposit that much money. Okay, so that is it for this first video. I'm going to stop there. There is a little bit of practice that uses just these two versions of the formula where we're looking at future value. I'm going to do a separate video that has some present value stuff. Um, so you can decide if you want to go through all your videos first and then hit the textbook for some practice, or pause here, do the practice that's tied to this video, and then find the next video. So your choice. Let me know if you have any questions.